Today we're going to take a more of a look into Chapter 9. This should probably round things off for us in terms of Chapter 9 content, but bringing in what we've learned about diprotic acid systems and fractional composition formulas, we should be able to approach what a buffer system might look like when it's made with a diprotic acid, which should introduce a new level of complexity, but hopefully through some careful reasoning and mathematical evaluation, we can do some approximating in appropriate spots to make this a little bit more easily digested content. First, to make sure we understand where we've been for the last few days, I want you to take a second to try and figure out what the pH of this solution of disodium or sodium monophosphate would look like. So go ahead and pause the video if you need to. Welcome back. So looking at this, I usually just cross out the sodiums. I don't like red. I usually cross out the sodium so that I know what I'm dealing with. For each sodium I remove, though, I'm going to add a minus charge. So HPO4 2 minus, you might recognize this from our previous work, but if you don't, 1H being present, this kind of looks like, to me, HA 2 minus, which would be the second intermediate of H3A or H3PO4, remembering that unless there's nitrogen atoms present, we're really not going to be protonating into the positive overall charge. So this being the second intermediate, I can just jump straight to my second intermediate formula, which should be the square root of K2, K3F plus K2, KW over K2 plus F. There were some questions about whether or not you should memorize this formula. I think it's useful to have it at your fingertips just once you've realized this is what your solution looks like, to be able to rattle that off. It'll just save time down the road. So try and work towards getting that into your memory. And then plugging in, I can go through the plugging in just to make sure we are all on the same page with our numbers. 10 to the negative 7.198 times 10 to the negative 12.375 times 0.5 plus 10 to the negative 7.198 times 10 to the negative 14th, all divided by 10 to the negative 7.198 plus 0.5. Again, that should have three significant digits, but I think I've written enough. And what we get coming out of that is 1.21 times 10 to the negative 10th molar, which would then yield a pH value of 9.917. Hopefully that was easy for you as it was for me. So looking today, I want to go back to our classic example of KHP that we just spent a lot of time with in our last video. Don't forget we've got PK1 of 2.950 and PK2 of 5.408, and we're going to abbreviate our three forms with H2P, HP minus, and P2 minus. If we're going to make a buffer out of this, the question becomes, I know that buffers have appreciable amounts of acid and conjugate base, or base and conjugate acid, but now the intermediate form is the conjugate base of the protonated form, and it's the conjugate acid of the deprotonated form, and the question of what happens when you approach equilibrium gets a little muddled. But we do remember that we do need to have that, and when we have that, our pH is close to our pKa. So this really means that for KHP, we're going to have two functional buffer regions. And if we just do a complete just linear extrapolation of what that model looks like, we can make two models of what a buffer might look like in a KHP situation. I know that there's one case where if I'm using the K1, I would be wanting to use HP minus and H2P, keeping in mind that K1 relates H2P and HP minus. And I could similarly from that, I could build a second equation where pH is equal to pK2 plus log of P2 minus over HP minus. Now this sounds a little bit confusing because, just to look at it, I've now made two equations that both have pH in them, and so are they equal to each other? No, they're not equal to each other. More what you should be looking at is that each of these has a time, has a situation where it is best used. And that's going to be the goal today. Reasoning out when these formulas get used, not trying to sit there and trying to solve both of them together. You can. It's lengthy and rather tedious to do, but it is possible. I've probably got it buried somewhere in my lessons and notes and emails. That full worked out solution for the diprotic buffer where you consider all three parts, but let's worry about the simple version first. So as we said, the buffer region is between 1 unit below and 1 unit above the pKa value. So we know for our monoprotic buffer formula, pH equals pKa plus log of A minus over HA. That would be like our acetate example we saw before. We have plenty of that. Old news. But this is why I'm bringing these images back. When we were to look at a diprotic formula, the two that I wrote would really be the two that we look at, and the question is, which one do I use in a given situation? So if I was just to draw the same lines again, here's our pK1 value in terms of pH. So I'm going to draw our lines. One's here, and then if we're going to go 1 unit above our second pK, that's going to be roughly there. I would draw a line 1 unit above pK1 and 1 unit below pK2, but they kind of overlap because our pKs are so close in this example that we've seen before. But as you can see, there's this tipping point where the alpha HA is maximized, and that really is going to be our switching point anyway. So I'm just going to draw our extra line here. So for really to answer which Henderson-Hasselbalch equation we should be using, it's more of a question of either looking at what substances you're mixing or what your target pH is. If your target pH is between 2 and 4, say, you're probably going to be wanting to use the K1 equation. And if your target's between just under 4 and 5.5, you'd be wanting to use K2. So really you're kind of saying if the target pH is close to pK1, use pK1's formula. Simple as that. Separately, if you're given in a problem that you are mixing two species, well, the two species that you're mixing dictate which K you use. Use the K corresponding to species. And hopefully, I'm going to go through some examples of both so that you see what it ends up looking like, but hopefully the logic is something that you can work for yourself, either going through this or checking your textbook or just working on some problems. So for example, here's a quick example that your book goes through. Here's an example where we're mixing KHP and sodium phthalate from a previous problem, actually. We want the pH of a solution where we mix 1 gram of KHP and 1.2 grams of sodium phthalate in 50 milliliters of water. Don't forget that the milliliters of water part kind of irrelevant because we're not worried about molarity as so much as we worry about moles. So given that this is HP minus and P2 minus, I know that that's K2, whose reaction is HP minus, will be in equilibrium with H plus and P2 minus. So I can kind of jump straight to solving this where I know what the pH is going to be because pH is equal to pK2 plus log of P2 minus over HP minus. Always, when we're using acid Ks, it is always base over acid. So plugging in some actual values for this, we have 5.408 from back a couple slides ago, plus log, and I'm not even going to try and calculate the moles. I'm just going to write the big fraction here and let my calculator do the work. And this should be 1.00 grams divided by, what was it, 210.094. I know that we're using the full molar mass of the sodium compound, but that's because we're using the mass of the full sodium-containing compound. We usually ignore the counterions, but in terms of mass, they can't be ignored. Divided by 1.20 grams, sorry, that's grams per mole, divided by 204.221 grams per mole. And grabbing a calculator and working that out, what you should get is a pH of 5.47. I think there should probably be one more significant digit there, but that's as far as I went when I made my notes. So shame on me for that, but there should be another digit there. To look at some other problems that where this would come into play, I want to look at this oxalic acid system. So here we've got our pK values 3 units apart, so it should be a little bit clearer as to what types of pHs we're going to be making a buffer with this. This is a fairly acidic acid in terms of the pK values, so probably these are pretty acidic buffers that we're going to be making. How many milliliters of 0.8 molar base should be added to 3.38 grams of oxalic acid to give a pH of 4.40 when diluted to 500 milliliters? Well, this sounds like one of those problems where, since I'm adding base, what's going to be happening is I'm going to have our H2-ox, as they abbreviate, and I'm going to add hydroxide, and that's going to do a one-way reaction to create the intermediate and water. And similarly, I can add base to the intermediate, and that would cause full conversion to the fully basic form. And so what's interesting about this is we can actually use the hydroxide to create the other component of the buffer. Now the question is, do we want a buffer that contains these two species, or do we want a buffer that contains these two species? And this goes back to our graph again, where if we're looking at our buffers, this is something I forgot to mention. Yes, you might be worried about the third component, the one that we're not mentioning. See, this K1 equation only uses H2A and HA minus, and this one only uses HA minus and A2 minus, but it's always true that all three species are in solution. However, looking at the third species, so to speak, this area down here and this area down here, these species always represent a minimum in terms of the overall composition, and so therefore this is where we start sweeping things under the rug, and we're going to say, let's not worry about these tiny bits. This is a situation where your pK units are fewer than 2 apart, and so in our other example where they're a full 3 units apart, these bottom ends of our graph are going to be even smaller when we're talking about a system predominated by the K1 equation or the K2 equation. So, the real question is, when do we stop using one and start using the other? And to look at that, back at this graph, I said that the tipping point would be useful where we were at the maximum concentration of intermediate. And luckily, we have a formula that actually tells us the maximum concentration pH. If you're starting with HA minus, we have our intermediate form for a diprotic acid where we know that H plus is equal to K1, K2, F plus K1, KW over K1 plus F. But I think it's really obnoxious to type this all into your calculator for something where you're just trying to figure out quickly what the pH is in terms of setting up the equations that you want to use. So let's apply some reasonable approximations. Whenever I see a plus sign in an equation, if I can make a reasonable determination that one of the two terms is significantly larger than the other, then I can ignore the smaller one. In other words, 1,000 plus 1, yes, it's 1,001, but the 1,000 is definitely the dominant component of that addition, and depending on significant digits, the 1 won't even factor in. 1,000 plus 1 is basically 1,000, where the 1 falls into the uncertainty region for your first measurement anyway. So looking at the top, can we say something about K1, K2F and K1, KW? Well, the real comparison that we're going to make here is, since the K1's present for both, we'll be looking at K2F and KW. And for most solutions, well, here's the thing I'm going to say. If F is large, then K2F will be larger than KW. For a sufficiently concentrated solution, for sufficiently concentrated, I'm saying anything over 0.01 molar is sufficiently concentrated. And then for the denominator, we're going to look at K1 versus F. Well, again, if we have a sufficiently concentrated solution and F is large, those are the approximations I want to make. And again, even if you don't think that F is sufficiently large, this is still a quick approximation step for making your buffer and figuring out which K equation to use. What that would give us once we cancel out the smaller terms is that H plus is equal to K1 K2F over F, which would cancel out. So that H plus is equal to the square root of K1 K2. And if we were to take the negative log of the whole expression and then do a little bit of algebra, what we would get is that pH is equal to 1/2 pK1 plus pK2. And this formula would work, again, in cases where F is large, or I guess in cases where K1 is small or K2 is small. Are those cases all the time? Well, no, but it would definitely be simpler to make that as a first step. So in our monoprotic system, we saw that the pH equals pK is our tipping point where the major species is present, but also our buffering region is on either side of that. And then over here, our buffering regions are on either side of that again. So basically, if we know what pH we're shooting for, that tells us what K value we're going to use. And then this pH right here is the average of the pK values. So working our way back to oxalic acid, I know that the average of these two values is going to be 2.758. So working my way back to the original problem, if we're adding KOH to 3.38 grams of oxalic acid, so we're starting with this H2OX. Based on the fact that 2.758 is our tipping point and our target pH is 4.40, then I know that my buffer is going to be a K2 dominated buffer that contains HOX and I need an eraser, and the oxalate anion. I believe I had written down it was originally 3.38 grams, which is going to be pretty important. So this means that in this equation, we're starting with the fully acidified form. We're going to be adding hydroxide, and we're going to create the intermediate. But that's not going to be sufficient. In fact, we don't want to do this halfway to create a mixture of the acid form and the intermediate form. We want a mixture of the intermediate form and the basic form. So we want to do this reaction 100%, and then we want to do this reaction less than 100%, so that the oxalate ion that we create and the intermediate form that we don't react stay mixed to make our buffer. So this will be less than 100%. So we're going to look at both of those. Now, if I had a different problem where our target pH was 2 or 1.5, well, in that case, I would probably not be using the second equation at all, and I would just be using K1. And so the problem would look different. And the real problem, the real issue with tackling these problems is on a case-by-case basis, you constantly have to ask, what's the target pH? Where did I start in terms of my acid species or base species? And what math and what chemistry has to take place to create the mixture that I want to have. So first, we should probably take a look at this. How much base is needed to convert 100% of the acid into the intermediate? And so this 3.38 comes into play because that's the amount of acid that I have, and they tell me that the formula mass is 90.035 grams per mole. And so that should give me 0.0375 moles of acid, which means for a 1-to-1 reaction, I'm going to need 0.0375 moles of hydroxide for this first step to take place. To figure out how many milliliters that is, I knew that it was a 0.8 molar solution, I believe, so 0.8 molar and from that we can calculate that our volume, we'll call it V1 because it's our first step, is equal to 46.9 milliliters. So that much base will convert 100% of the acid into the intermediate. That means if you add twice that much, you would probably get a full conversion into 100% base. We don't want to do that, so I know that when I'm done with the second part, I should have a number that's less than 46.93. If I don't, then I made a mistake somewhere. Right. So at this point, I think the best way to approach this is if we're going to take a solution of intermediate and convert some of it into the full base, then I want to draw one of these ICF tables that I've mentioned in class before. So starting with the intermediate and adding hydroxide, I'm going to make that and water, the initial, the change, and the final. So we're going to say our initial value is left over from the previous problem, because once we've added this many moles, we've created that many moles of the intermediate. So that's 0.0375. I have X moles of base that I need to add, and so when I react X moles of base, I will create X moles of oxalate, and like I said, we want the hydroxide to run out. We don't want to fully consume the intermediate, so this will be 0.0375 minus X. From this point, we can plug this into the K2 equation here. And then we can start putting in some numbers. We have 4.40 nope, can't talk and write at the same time, not always. We have 4.40 as our target pH. The pK2 for oxalic acid is 4.266, so we're in the right ballpark. Just plugging in the values from our ICF table, the amount of oxalate at equilibrium is X, and the amount of the intermediate is 0.0375 minus X. So again, this is one of those situations where your setup is going to vary from problem to problem, but you have to be careful to actually process your data correctly. It's the setup that matters more than almost anything else, and that's why I'm spending all this time to get the setup right so that I know my answer will be correct. So going through algebra and just I made a mistake. I'm going to go back and erase some stuff. I'm sure some of you have looked at this already and said, you forgot something. If you did, good for you. You can feel free to comment below and say, I forgot something if you haven't already. This is not the Henderson-Hasselbalch equation. I forgot a little word. There we go. And then this is log. That would make a very large difference in my calculated answer. So before I finish my problem, again, if this was a problem where my target pH was closer to K1, well, I would just have gone to this step immediately, and I would have skipped the previous step where I did all the stoichiometry to figure out that V1. In that case, there would only be one V. But yes, if I go through to solve and do some algebra, what I end up here with is X is equal to 0.0216 moles of OX2 minus, which is equal to that same number of hydroxide. Keep in mind that we have 0.8 molar solution, so 0.0216 moles over, and we're going to call this V2 since we're in the middle of the problem. This is our second V, and V2 in this case should be equal to 27.05 milliliters, which is good because that's less than the 46.9, so that makes me a little bit hopeful that I got an answer that makes sense. This answer should also kind of make sense, so if 47 milliliters does the full conversion, knowing that my pH here is 4.40, which is slightly larger than pK2, means we're going to have a little bit more base than acid, so that this number should be slightly larger than half of the 47, and it is, which is great. So now we can go through, and to find our total volume needed to accomplish this, you just have to add your two volumes, which would be 46.9 milliliters plus 27. And our total volume needed to carry this out would be 73.9 milliliters. So if I add 73.98 milliliters of 0.8 molar potassium hydroxide to 3.38 grams of oxalic acid, I should result with a buffer that has a pH of 4.40. So that kind of encompasses the two types of problems we'll see. We've got problems where you are told amounts of acid and base, conjugate acid and conjugate base, and you have to analyze the chemistry of the compound in question. And then you've got your other problems where you're adding strong acid or strong base to a compound and creating the conjugate. But now that it's a diprotic buffer, there's the question of which conjugate system is the conjugate system that you're looking for. So to wrap this up, or to put everything into words, we've got kind of four options. And we'll split them up into 1, A, and B. So the first situation you're going to see is you start with the fully acid species. And I'm only talking about the situations here where we're adding strong acid or base to your compound, and I'm not mixing the conjugates themselves. So if target pH is less, or it's not less than, it should be, if your target pH is, oh, you know what, no, I am going to say less than. If it's less than 1/2 pK1 plus pK2, then use K1, Henderson-Hasselbalch, V equals answer. Just the volume that you get. For letter B, if the target pH is greater than the average, you find V1 with stoichiometry, use K2 to find V2, and then your total is equal to V1 plus V2. And then in the second case, you can make a buffer if you start with the base. And then again, if you're, so I'm going to approach this from the other way. If the target, you know what, I'll do it the same way. If you start with the fully basic form and your target pH is still less than the average of your pKs, that would be akin over here to starting over here and moving to a pH that's around this area. So you can see that your mixture is going to be made up of HA minus and H2A minus. So again, you have to use stoichiometry to find an equivalent. You're going to use K1 because that's the formula that dominates the solution that you've now made. You're going to transition to the intermediate and then keep going to make some of the fully protonated. And then the total is the sum of the parts. And then I'll write it over here to make some more room. if the target pH is greater than the averages. Whoa. Again with this talking and writing. That would be like starting again with this base on the far right, but then our target pH is actually just more in this region. So the two species are going to be A- and A2-. Then you're just going to use the K2 Henderson-Hasselbalch, and then V is the answer. So really there's 4 cases, 2 of them that are 2-step problems and 2 of them that are 1-step problems. As a summary, to make sure that you understand what you're doing here, I'm going to let you all solve this one on your own. This would be probably a good homework problem, but just to give you a leg up on solving this, for each of these cases, we're going to do 3 separate cases. The one thing I should tell you is that the average of the pK values in this case would be 8.34, and that should be enough to really get you going on how to approach this problem. Thanks for watching.